All right. So like I was saying, we're discussing, I don't know if I was, did you guys see this part? Please let me know so I can start here. I think it's safe enough to start here. All right, all right. I'll start here then. So like I was trying to say, there's two categories of radiation. It can be ionizing or non-ionizing. All right. Ionizing radiation is the one which is able to knock out electrons from an atom. All right. So that is the process of ionization. Whereas non-ionizing does not have sufficient energy to remove or to knock out electrons from atoms, all right, or from the shells. Now, examples of ionizing radiation. So this ionizing radiation is further divided into two. All right. So we have directly ionizing, which is basically charged particles. All right. So this can directly deposit their energy into matter. All right. Examples of those would be electrons, which are positively charged, electrons, which are negatively charged, protons, which are positively charged, and alpha particles, which are a bit heavier, but still positively charged. All right. So those are charged particles, whether positively charged or negatively charged. Indirectly ionizing radiation is the one that does not deposit their energy directly into matter, but first they have to form secondary ions. All right. So they have to create charged particles first, and then those will deposit the energy into matter. So, for example, we have photons, which is basically an electromagnetic radiation, like X-rays and gamma rays. All right. X-rays basically are formed from bremsstrahlung or characteristic radiation, which we will discuss a little bit later. Whereas gamma rays are formed from nuclear decay or just radioactivity. Okay. So X-rays are formed from basically the interaction between electrons and the nuclear or the nucleus. All right. And then gamma rays are simply from the decay or the transition from a higher energy state of the nucleus to a lower energy state, and then you can form gamma rays. For those of you who have done nuclear physics or atomic physics, you may understand this much easier. Neutrons as well are indirectly ionizing radiation. They are also neutral particles with a zero charge. So what does it mean to be indirectly ionizing? Well, it simply means for energy to be deposited, there has to be charged particles formed first. Remember, indirectly ionizing radiation is neutral radiation. So it cannot directly deposit energy. So first it has to knock out some electrons, and then those are the ones which will deposit the energy into matter. All right, so they deposit energy in two steps or stages. All right. Those are the examples of ionizing radiation. Non-ionizing radiation, of course, is the one which is not able to eject any electrons out of atoms. So I was about to ask a question when my network dropped. So I was trying to ask examples of non-ionizing radiation. If there's anyone who knows in the chat, you can type in the chat if you know the differences between if you know some of the examples of non-ionizing radiation. Microwave, that's correct. Anything else? If you remember your electromagnetic spectrum, visible light, that's correct. Anything else? Any other type of non-ionizing radiation? RF, that's correct. Radio waves, yes. Infrared, that's correct. One more. UV, right. But now we should also remember that UV actually comes in three bands. So there's UVA, UVB, and UVC. So UVC sort of straddles the border between non-ionizing and ionizing radiation. So actually UVC can ionize atoms, and it's sometimes considered to be near the ionization threshold. All right. So in terms of the energies required to ionize matter, um, basically we can characterize this in terms of the energy or the wavelength. So the wavelength threshold between non-ionizing and ionizing is basically 100 nanometers. So anything above 100 nanometers is considered to be non-ionizing. All right. Whereas anything below 100 nanometers is considered to be ionizing radiation. As you know, the energy of radiation and the wavelength, these two are inversely proportional. Let me try to put a laser pointer here. I think it will make things easier for you. So anything above 100 nanometers or less than 10 electron volts, which is like the corresponding energy, that would be non-ionizing. Whereas shorter wavelength radiation or less than 100 nanometers would be considered ionizing radiation. And this would correspond to about 10 electron volts. So anything higher than that is able to remove electrons from atoms, all right, which is what we call ionization. Anything less than that, we can only excite the atoms, all right? So there's not going to be any electrons knocked out, but they can vibrate or they can be excited to a higher energy state, but they simply drop back to their original ground state without leaving the atom itself. All right, are we clear so far? All right, this should be something you might have done already in undergraduate physics. All right, so let's talk about some categories of ionizing photon radiation. All right, so we have focusing on photon radiation right now. Okay, so either X-rays or gamma rays. Okay, that's what we are looking at right now. So we are looking at ionizing photons. Now we have four broad categories. So we can get photons from characteristic radiation, which is basically as a result of electronic transitions between atomic shells. All right, so as you know, atoms are, or electrons are exist or they inhabit shells, all right? And any movement of electrons between a higher energy shell to a lower energy shell, meaning from an outer shell to an inner shell, all right, moving towards to the nucleus. So shells that are outermost shells are considered higher energy shells, whereas those which are closer to the nucleus are considered to be more stable and they've got a higher binding energy. So if an electron moves from a higher shell to a lower shell, of course, there's an energy difference between those two shells, and that energy would be emitted as characteristic X-rays. So that energy is simply the differences between those two electronic shells. All right. So, for example, if a shell transitions from the L shell to the M shell, all right, the L shell being the outer one, the M shell being the one closer to the nucleus, energy would be lost in the form of characteristic X-rays, and that energy would be equal to the differences in the binding energies between the L shell and the M shell. All right, so that's characteristic radiation. Bremsstrahlung radiation, on the other hand, results from the interaction between electrons and the nucleus. All right. So if an electron approaches the nucleus, so let's say there's an incident electron with a certain kinetic energy, and it approaches the nucleus, it's going to be attracted through Coulombic interactions, right? As you know, the nucleus is positively charged because of the protons, and the electron is negatively charged. So what happens is there's going to be Coulombic interactions between the electron and the nucleus. So that electron is going to be slowed down, all right, from its original kinetic energy or velocity. And then that slowing down energy is emitted as Bremsstrahlung radiation. So it's emitted in the form of a photon or an X-ray photon, all right? So that's Bremsstrahlung. Bremsstrahlung actually is from a German word, which means braking, like the same way you apply brakes on a car. So Bremsstrahlung means braking radiation from the fact that the incident energetic electron is slowed down by the nucleus. And that energy is emitted in the form of an X-ray photon. All right. Now, the third category is gamma rays. Gamma rays, these are emitted from nuclear transitions or from radioactive decays. All right. So if you've got an unstable nucleus which decays to form a more stable nucleus or even to a ground state, then a gamma ray is emitted. All right. So this is another type of a photon. By the way, there's no real difference between an X-ray and a gamma ray besides their origin. So the only difference between X-ray photons and gamma ray photons is their origins. So gamma rays are formed from decay, whereas X-ray photons are formed from either electronic transitions between shells or electron nucleus interactions. All right, so once they are formed, you cannot tell the difference between the two. The only difference is where they originate. All right. Now, the last category is annihilation quantum, or what we call annihilation radiation. This basically results from the interaction between, let's see here, just wanted. So annihilation quantum or annihilation radiation is basically as a result of matter and antimatter type of interaction. All right. So if you have a particle and an antiparticle, meeting together, then they would annihilate each other. All right. So the most popular one is the positron electron annihilation phenomenon. So a positron, you can think of it as a positive electron, whereas an electron is simply an antiparticle of that, which is negatively charged. Same mass, but opposite charges. All right. So now in the electron positron annihilation, what happens is when they meet, they actually both disappear. And then their rest mass energy, right? The rest mass energy is then converted into two gamma ray photons. And those two gamma ray photons, if you remember maybe from your undergraduate physics, the rest mass energy of an electron is what? You type in the chat. I just want to make sure we're on the same page. What's the rest mass energy of an electron or a positron in MeV? Anyone? Can you type the rest mass energy of an electron or a positron in MeV? You can type in the chat or you can unmute yourself. Or you can even tell me just the formula. How do you calculate the rest mass energy? Right, 0.511 MeV, correct. So that's the rest mass energy of a positron or an electron. So once these two annihilate, these particles both disappear. And what happens is now they convert, right, their rest mass energy into two gamma ray photons, right? As you know, the rest mass energy is basically given by the formula E is equals to what? MC squared, right? So that is equals MC squared. If you calculate it to give you the 0.511 MeV, as you correctly indicated in the chart. So now those two gamma ray photons, so remember these are um, um, gamma ray photons produced from the conversion of mass into energy. So basically their mass is converted into energy through the equation E is equals to ME squared, MC squared. Right? So energy now is equal to their mass times the speed of light squared, which will give you this 0.511. So that's the energy of the photons produced. And these photons are produced at 180 degrees apart. So they basically travel in opposite directions. So is there anyone in the chat who knows where positrons may arise? Do you know where some certain typical sources of positrons? We know electrons, of course, they exist naturally in atomic shells. Does anyone know any sources of positrons, whether artificial or naturally occurring? The answer is actually there on the slides. So we can get positrons either from positron emitting radionuclides, which are used in PET. Yes, beta plus decay, that is correct. So we can actually get positrons from beta plus decay. But we can also get those from positron emitting radionuclides. These are the radionuclides that are used in PET. PET is actually short for positron emitting tomography. All right, so those radionuclides that emit positrons would be, an example would be fluorine 18 or F18. All right. I know you do medical imaging. You cover that part in nuclear medicine, where you look at PET as an imaging modality. So those are used as well to image the patient from within. So those are actually injected into the patient. So that's one source of positrons. And as you said, also beta plus decay is another source of electrons, sorry, of positrons. And when those positrons meet electrons, they will undergo annihilation. So they will disappear, and two gamma ray photons of 0,511 MeV each will be emitted in opposite directions. All right, I hope we are clear so far. Now, let's move on to a few definitions. All right, a few definitions. And you will see these terms frequently throughout the course. So exposure, what is exposure? Well, exposure here, this is given in a formula form, but basically exposure basically measures the ability of photons to ionize the air. All right, so what it quantifies is the total electric charge Q that is produced per unit mass of air. All right, so this is the total electric charge which is produced per unit mass of air. So exposure basically quantifies the ability of photons to ionize the air, all right, to produce whatever charge for a mass of a given quantity of air. The SI unit for exposure is Coulomb per kilogram, all right? Coulomb representing the charge, and then so charge per unit mass of air, so Coulomb per kg. That's the SI unit. The traditional unit or the old unit is the Röntgen, which is R. All right. The Röntgen basically can be related to the SI unit, coulombs per kg. So one Röntgen is basically 2.58 to the negative 4 coulombs per kgs of air. All right. So that is the conversion from one Röntgen to the SI unit of coulombs per kilograms. What else? Now let's look at dose, or what we normally call absorbed dose. All right. So when you say dose, it normally we normally just talk of absorbed dose. I'm thinking of, let me I just want to switch on my webcam because I don't think any of you have seen me. um can you see me? Right. In case you are guessing if you are if a ghost is speaking to you. So here I am. So let me move on. So dose, which we normally just call absorbed dose, is basically given by this equation here. So it's basically the amount of energy which is deposited per unit amount of or unit mass basically of medium. All right, so that is a definition of absorbed dose. All right, the SI unit of dose is what? Is joules per kgs. So that is the SI unit. In terms of the old unit of dose was rad. So in some textbooks, you will see this unit, radians. So the rad is basically not the radians on your calculator, by the way. So this rad is basically equivalent to 0.01 gray. Or you can put it this way: 1 gray is equals to 100 rad or rads. All right. So that is the old unit. So in case you see this unit in your textbooks, don't panic. That was the unit used for absorbed dose. All right. Let's talk about equivalent dose. So equivalent dose basically it takes into account the type of radiation. All right, the type of radiation. As I showed you before, there's different types of radiation, right? You have got I think I moved this. You have got photons, neutrons, electrons, you've got alpha particles, all right? So all those different types of radiations, they've got different biological impact, all right, on the tissue, or it has got different biological damage to the tissue. So when we talk about equivalent dose, we are actually taking into account the biological detriment of that particular type of radiation. So that is the reason why we actually introduced a weighting factor of WR, which is the radiation weighting factor. So it takes into account the type of radiation. So for example, for photons and electrons, the radiation weighting factor WR is equal to 1. All right. So for electrons and photons, the weighting factor is 1, which means the absorbed dose would be equal to the equivalent dose in that case. For neutrons, the weighting factor would be, it's actually a range from 5 to 20. And the weighting factor for neutrons actually depends on the energy of the neutrons. All right, so the damage would be proportional to the energy when you look at neutrons. All right, we'll look at neutrons quite a bit, just to look at how they in terms of the radiation protection aspect of things. All right. So the unit for equivalent dose is CVET. That is the SI unit. But the old unit is RAM. So just like rads, it's actually 0.01 of a CVET. Okay, or you can put it this way: 1 CVET is actually 100 rams. Right, so that's the traditional or the old unit. So you may see this in certain books, but all new textbooks actually just use the newer units. But of course, you may be expected to convert from one to the other. In case you are given a quantity in these old units, you need to use this conversion. You simply have to divide by 100. All right. Now, the last one is activity, which is something you are familiar with, I guess, from nuclear physics. And of course, activity is simply the amount of disintegrations that occur basically per second. All right. So this is the decays, or the number of decays per second. So you can define it as a formula. So it's basically the decay constant lambda times the number of nuclei that are available at that given point in time. So it's a function of time. And so the units of activity is becquerels. A becquerel is basically a decay per second. That is why the unit is per second. All right, so 1 becquerel is 1 decay per second. The old unit, which is pretty much used even today, is the curie. And 1 curie is basically 3.7 gigabecquerels, all right, or 3.7 to the power 10 decays per second. all right? And you can, of course, express becquerel as in terms of curies, which is simply 1 over 3.7 to the 10. All right. Now let's just look at some basic definitions and some illustrations of atomic structure. All right, so as you may know, we in the atom, we've got 3 main constituent particles, which is the proton and the neutron, which both reside in the nucleus. And we also have got the electrons, which reside around the nucleus in the atomic shells. All right, so the protons and neutrons, these are called nucleons for the simple reason that they dwell in the nucleus. All right. And the atomic number is basically the number of protons or the number of electrons if the atom is electrically neutral. All right. So if the atom is not electrically neutral, then the atomic number won't be equivalent to the electrons, because if you knock out an electron, then of course, the atom will be positively charged. So the number of electrons would no longer be equal to the number to the atomic number. All right. So when we say number of electrons here, we are assuming the atom is electrically neutral. All right. So in that case, protons will be equal to electrons. That will be equal also to the atomic number Z. All right. And of course, we have got what we call also the mass number, given by the symbol A, which is simply the sum of the nucleons, Z, which is the protons, and N, which is the neutrons. All right. So the nucleons, the sum of the nucleons basically gives you the mass number. All right. We say mass number because the mass of the atom basically is concentrated in that nucleus. The electrons don't really contribute much to the mass of an atom. So when you talk about atomic mass number, we are specifically referring to the nucleus of that atom. All right. And again, I want to just show you like a conventional illustration of how we, I don't know what happened here. The conventional way of illustrating an atom, right? So let's say an atom is symbol X and mass number A and atomic number Z. That's the way we would represent this. All right. An example is cobalt-60 with 27 protons. That will be equal to the atomic number here at the bottom. And of course, the mass number would be the protons plus the neutrons, 27 plus 33, and then you get 60. That's the mass number. All right. So these are simply the basics of atomic structure. All right, let's jump to nuclear structure. All right, so like I said before, the atomic mass is concentrated in the nucleus. All right. Of course, the number of neutrons would be A minus Z. All right. And the nucleons, which is the protons, the nucleon, and the neutrons, these are bound to the nucleus by what we call the strong force. Again, this is nuclear physics stuff, which you should cover as well. So I'm not going to waste too much time on that. And in terms of the strength of the force, it's actually very dependent on the range. So it's a very short range force. So it's only effective within a few femtometers. All right, a femtometer is basically like 10 to the power minus 15 of a meter. So it's a very, very short distance. All right. So the strong force in the nucleus is only effective within a few femtometers. All right. And if you want to calculate the radius of a nucleus, you can estimate from this equation, which is basically a function of the mass number. All right. So it's basically the nuclear radius constant times the mass number to the power 1 over 3. All right. Or the cube root of the mass number. And of course, this is a simple equation. We're not going to waste time on these things. We can calculate the mass deficit or the mass defect. All right. And we can calculate that from the individual, this basically the sum of the individual components of the nucleus, and subtract that from the mass of the entire nucleus. So if we take the mass of the proton, all right, so when you say mass sums of these individual components, we are talking about protons and neutrons. So if we take protons and neutrons and we sum them together, we get their total mass, and then we subtract that total mass from the mass of that nucleus. Then we'll get what we call the mass deficit or the mass defect. And when we convert that mass defect, right, we convert that mass into the energy equivalent using Einstein's formula, E is equal to mc squared, then we would get the total binding energy, all right, of that nucleus. So basically, this would be the mass of the proton, all right, times the Z. Z is the number of protons. So basically, this is the total number of protons. So the mass of each proton times the total number of protons, Z, we get the total protons, convert that into energy, right? You do the same for neutrons. Remember, neutrons is the mass number minus protons. And then you get the total number of neutrons times the mass of each neutron. You get the total number of, the total mass of neutrons. You convert that into energy, all right? And then the capital M is simply the mass of the nucleus, M, all right? So basically the sum of the individual components minus the mass of the nucleus itself converted to energy would give you the total binding energy, all right? Are we clear so far? I hope I'm not rushing too much. I'm assuming this is stuff that you are at least partly familiar with. All right. So I don't want to spend too much time on this. All right. So please confirm if everything is good. Thumbs up, or you can, stop me at any point. Right. So let's move on. So if you plot the binding energy per nucleon, which means the binding energy per mass number of that atom, then you get this type of graph. All right. Basically, below A is equals to 56. So on the x-axis, you've got the mass number, and then on the vertical axis here, you've got the binding energy per nucleon. All right. So around the A is equals to 56 here, beneath that point, right? So from here all the way going down, you'll see that the binding energy per nucleon increases with the mass number, all right? And the reason for that, of course, is because the nuclear force increases with increasing atomic number, all right? Or with the increase in the number of or the mass or the size of the atom, all right? So in that case, it means fusion is favorable in this zone here. So below A is equals to 56, the binding energy actually increases, all right? And of course, once you get to a certain point, the strong force, right? Remember, we spoke about the strong force, which is dependent on the size of the atom. The strong force begins to balance with the size of the nucleus. So what happens as you increase the number of protons in the nucleus, they begin to repel. So as the atomic number or the proton number increases, the Coulombic repulsions actually begin to increase. And at some point, they start to balance out with the strong force. And from then on, all right, at approximately A is equals to 60, from this point going forward, that's where you begin to see a decrease in the binding energy per nucleon. So what happens there is that the Coulombic forces between protons actually begin to increase. So now there will be a repulsion between protons in the nucleus. And in that case, that will mean fusion is no longer favorable, but now fission or breaking apart is now more favorable. All right. So as fission dominates, the binding energy decreases. And that's where we start to have also unstable nuclei that are more prone to undergo fission rather than fusion, right? You can take a look at these spikes as well as just for your homework, just to look at why these spikes here exist. Well, so this is something I just recommend you should go take a look, all right? But here are some examples of the binding energy per nucleon. So for hydrogen, it's about 1. So this is deuterium, or it's like an isotope of hydrogen, okay? This is tritium with a mass number of 3, but still it's a hydrogen isotope, all right? But as you see, the binding energies per nucleon are different as we increase the mass number, all right? The number on top here, all right? For helium-4, of course, it increases, and then cobalt-60, it increases to about 8,8. All right, so this is like the maximum you can get. So 8,8 is like the maximum binding energy per nucleon that you get. And of course, as you see, uranium-238, it has a much larger mass number, but then you see its binding energy per nucleon is a bit lower. This is because this is a large nucleus, and of course, there's more repulsions. That's why the binding energy per nucleon for uranium here is much lower than cobalt-60. Right. Nuclear reactions, of course, you can bombard a target with certain projectiles. Just as an example, you can bombard with, for example, you can bombard cobalt-59 with neutrons, and you get cobalt-60. All right. And of course, in every reaction, there are products. So A represents the target. Capital A is the target. Small a is the projectile. Capital B is the daughter nuclei, and also small letter b for the products of that nuclear reaction. All right. So of course, in every nuclear reaction, there are certain physical quantities that will be conserved. All right. The charge, mass number, the momentum, as well as the mass energy. Those will be conserved, all right, from the simple conservation laws. All right. I want us to take like a short break. And then I think we should start at 6:01 or so. I think 6:01 is good. It's 5:51 now. So let's take a 10-minute break, and then we will continue. All right. Let me share my screen once again. All right. I hope you can see my screen. Let me. Yeah. Right. You can see my screen, right? Okay. So I think we left off on nuclear reactions, right? So let's just move on to radioactivity very quickly. So we want to cover all the basics as much as possible today, so that when we start clinical work or clinical related physics, it should be easier for you guys.